Namaskar, I am Dayan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the linear equation with constant coefficient from the ordinary differential equation of MSc post, semester post. Definitions of linear differential equation with constant coefficient. A linear differential equation of order n with a constant coefficient is an equation of the form a naught y raised to n plus a1 y raised to n minus 1 plus a2 y raised to n minus 2 plus dot 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 plus a n y is equal to b of x, where a naught is equal to 0, a1 a2 dot 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 a and are complex constant and b is complex valued function on an interval I. A less than x less than b, the operator L defined by L of phi of x is equal to phi raised to n of x plus a1 phi raised to n minus 1 of x plus a2 phi raised to n minus 2 of x plus dot 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 plus a n of phi of x is called as differential operator of order n with constant coefficient. The equation L of y is equal to b of x is called non-homogeneous equations. If b of x is equal to 0 for all x in I, the corresponding equation L of y is equal to 0 is called homogeneous equations. Next, initial value problem for several second order differential equation. Uh, Here L of y is equal to y double dash plus a1 y dash plus a2 y is equal to 0, where a1, a1 and a2 are constant. Let theorem now here theorem let a1 a2 are constant and consider the equation L of y is equal to y double dash plus a1 y dash plus a2 y is equal to 0. If R1 and R2 are distinct roots of the characteristic polynomial P1 of P of R is equal to R square plus A1R plus A2, then the function phi1 of x is equal to e raised to R1x and phi2 of x is equal to e raised to R2x. Our solution of L of y is equal to 0. If R1 is repeated roots of the characteristic polynomial P of R, then the function phi1 of x is equal to e raised to r1x and phi2 of x is equal to x into e raised to r1 of x are the solution of L of y is equal to 0. For proof, let phi of x is equal to e raised to rx be a solution of L of y is equal to 0. That is L of e raised to rx is equal to e raised to rx rs star plus a1 e raised to rst plus a2 I raised to rx. Therefore is equal to r square plus a1 r plus a2 into e raised to rx. That is L of e raised to rx is equal to 0 if and only if p of r is equal to r square plus a1 r plus a2 is equal to 0. If r1 and r2 are distinct roots of p of r, then L of e raised to r1x is equal to L of e raised to r2 of x is equal to 0, and phi1 of x is equal to e raised to x r1x and phi2 of x is equal to e raised to r2x. Our solution of L of y is equal to 0. If r1 is a repeated root of p of r, then p of r is equal to r minus r1 square and p dash of r is equal to 2 into r minus r1. L of e raised to rx is equal to p of r into I raised to rx for all r and x. Dou by dou r of L of e raised to rx is equal to dou by dou r of p of r e raised to rx. L of x into e raised to rx is equal to p dash of r plus x into p of r into e raised to rx. At t is equal r is equal to t1, p of r1 is equal to p dash of r1 is equal to 0. Therefore L of x into e raised to r1x is equal to 0. Thus this showing that x into e raised to r1x is the solution of L of y is equal to 0. L of y is equal to 0. Thus, if R1 is repeated roots of the characteristic polynomial P of R, then phi 1 of x is equal to e raised to R1x and phi 2 of x is equal to x into e raised to R1x. Our solution of L of y is equal to 0. Theorem, next theorem. If phi 1 and phi 2 are two solutions of L of y is equal to 0, then C1 phi 1 plus C2 phi 2 is also solution of L of y is equal to 0, where C1 and C2 are any two constant. Proof: let phi 1 and phi 2 be two solution of L of y is equal to 0. That is, L of phi 1 is equal to phi 1 double dash plus A1 phi 1 dash plus A2 phi 1 is equal to 0. L of phi 2 is equal to phi 2 double dash plus A2 phi 2 dash A1 phi 2 dash plus A2 phi 1 is equal to 0. Suppose C1 and C2 are any two constant, then the functions phi defined by phi is equal to C1 phi 1 plus C2 phi 2 is also solution of L of y is equal to 0. Therefore, L of phi is equal to A phi 1 plus A2 phi 2 double dash plus A1 A phi 1 plus C2 phi 2 plus A2 A phi 1 plus A2 C2 pi 2 is equal to C1 phi 1 double dash plus A1 phi 1 dash plus A2 phi 2 1 plus C2 pi 2 double dash plus A1 phi 2 dash plus A2 pi 2 is equal to C1 L of phi 1 plus C2 L of phi 2 is equal to 0. Function phi which is 0 for all x is also solutions called the trivial solution of L of y is equal to 0. The result of the above two theorems allows us to solve the all homogeneous linear second order differential equation with constant coefficient. Definition, next definition. An initial value problem L of y is equal to 0 is a problem of finding a solution phi satisfying phi of x naught is equal to alpha naught and phi dash of x naught is equal to beta naught, where x naught is some real number and alpha naught or beta naught are given constant. Next theorem, existence theorem here. For any x naught and constant alpha beta, there exists a solution phi of the initial value problem L of y is equal to y double dash plus a1y dash plus a2y is equal to 0, y of x naught is equal to alpha, y dash of x naught is equal to beta, minus infinity less than x less than infinity. By theorem, there exist two solutions phi 1 and phi 2 that satisfied L of phi 1 is equal to L of phi 2 is equal to 0. From this theorem, we know that C1 phi 1 plus C2 phi 2 is a solution of L of y is equal to 0. We show that there are unique constants C1 and C2 such that phi is equal to C1 phi 1 plus C2 phi 2 satisfies phi of x naught is equal to alpha and phi dash of x naught is equal to beta. Therefore, phi of x naught is equal to C1 phi 1 of x naught plus C2 phi 2 of x naught is equal to alpha and phi dash of x naught is equal to C1 phi 1 dash of x naught plus C2 phi 2 dash of x naught is equal to beta. Uh, Above system of equations will have a unique solution C1 C2 if the determinant delta is equal to phi 1 of x naught, phi 2 of x naught, phi 1 dash of x naught, phi 2 dash of x naught is equal to phi 1 of x naught, phi 2 dash of x naught minus phi 2 of x naught, phi 1 dash of x naught is not equal to 0. Then by the theorem, phi 1 of x e raised to r1x and phi 2 of x e raised to r2 of x r2x are two solution of L of y is equal to 0 for r1 is not equal to r2. Therefore, delta is equal to e raised to r1 x naught r2 e raised to r2 x naught minus e raised to r2 x naught r1 e raised to r1 x naught is equal to r2 minus r1 e raised to r1 plus r2 x naught is not equal to 0. Therefore, by theorem, phi 1 of x is equal to e raised to r1 x and phi 2 of x, no, x is equal to x into e raised to r1 x are solutions of the L of y is equal to 0 and delta is equal to e raised to 2 r1 x naught, which is not equal to 0. Thus, the determinant condition is satisfied in both the cases. Therefore, C1 C2 are uniquely determined. This function phi, phi is equal to C1 phi 1 plus C2 phi 2 is the desired solution of the initial value problem. This is